everyone. My name is Robert Paxton, and I'm the VP of Strategy and Performance for Charles Taylor in Canada. Firstly, I'd like to thank everyone for attending our Mining 101 webinar. With close to 200 participants today, this is a great launch to our new Charles Taylor Canada Education series. We'll be hosting another 10 webinars with you over the next year, so please do look out for email invitations for the next sessions. I'd like to first cover some housekeeping items before introducing the presenters and the agenda for the webinar. So please note that this session is being recorded, and we will send all attendees a follow-up email after the presentation. That'll have a link to the recorded session. After this webinar, a short survey will pop up, which should only take 2 minutes to complete, and we'd be very grateful for your feedback. Just so that you're aware, all attendees are muted. However, we do encourage you to share questions that you'd like answered by typing them into the questions section in the drop-down menu. Regarding continuing education credits, the presentation is approved for CE credits for adjusters, brokers, and examiners. And at the end of the presentation, we'll provide an email address for you to contact to get your credits. We do ask that you include your CIPR or REBO number when you send the email. We've also included the bios of our speakers in the drop-down, so you can download those as well. In regards to the presentation itself, we're excited to share with you today. It's a collaboration between our Canadian and Australian teams, and we do hope that sharing perspectives from different geographic regions will be helpful for you. CTA has a great deal of global expertise with offices in over 30 countries, and we'll be continuing to share our local knowledge and global expertise with you in the upcoming webinars. So we have 3 presenters for you today. The first of which is Andy Milne. Andy is a senior engineering and resources adjuster who's based in Australia. He's a qualified mining engineer and has been an independent adjuster for 7 years. Andy's areas of expertise are complex, heavy industrial claims with a particular focus on mining, power generation, and refining. Our second presenter is Dallas Hirsche. Dallas is the Deputy Managing Director and Regional Head for Canada and is based in our Calgary office. He's been an independent adjuster for 30 years and has been involved in some of the largest losses in Canada. His areas of expertise are natural resources, upstream and downstream energy losses, utilities, commercial industrial property damage, business interruption, course of construction, and pollution liability. And our third presenter is Brian Aston. Brian is the Senior Vice President and manages our Vancouver office. He's been an independent adjuster for over 45 years, and his experience has taken him around the world managing major losses. His areas of expertise are natural resources, commercial industrial property, boiler machinery, course of construction, wrap-up liability, pollution liability, and business interruption. So before we move on to the agenda, we're going to start today's session by kicking things off with a quick poll. So the poll should pop up in a second. Here we go. Canada is the world's largest producer of which of the following minerals? Gold, diamonds, uranium, or potash? You can select which one you think is the correct answer now. We'll just wait a second, and once everybody's finished voting, we can pull up the answer. Okay, Jada, can we see the results? Okay, here we go. Perfect. Well, there we go. Most of the audience is right. It's potash. So just to give you some quick tips on potash. So potash refers to potassium-containing compounds that are mined underground. Canada produces roughly 21 million tons of potash in 2019, which accounted for 32% of the global production. And this is primarily from Saskatchewan. Total reserves in Canada are approximately 1 billion tons, and potash is primarily produced for fertilizers, but also detergents, ceramics, and pharmaceuticals. Okay, great. Thanks for participating in that. So for the agenda for today, this webinar will start with an overview of mining methods, including open pit mining, underground mining and block caving, and then move on to processing and tailings. We'll then cover mining risks and hazards related to COVID-19. And then we'll have a number of very interesting case studies from real-world claim examples. Finally, we'll have 10 minutes to answer any questions you'd like to ask at the end. So now I'd like to hand over to my colleague Andy Milne to start the presentation. Thank you.
Hi everybody, good morning. As Robert mentioned, before joining Charles Taylor, I was working in the mining industry, a qualified mining engineer. And today, really just want to cover basically start to finish of a mining operation, a typical mining operation. Appreciate some of the points that I'll cover today could be presentations on their own, but really the point for the technical side of this presentation is just to provide context, so that hopefully when you go back into your day-to-day jobs and you come across either claims on mines or risks on mines, you'll know where that fits in the wider mining process. And I'm just going to kick off with a simple look at open pit mining. I'll then cover underground before moving on to processing and tailings. In its simplest form, open pit mining follows the drill, blast, mine, and haul process. First stage is drilling. You can see in this image we have two types of drill rigs. These drill rigs are drilling blast holes in a bench on an open pit mine. The blast holes are then filled with explosives and detonated and then mined out. So just to give you some idea of scale, there's a couple of mining engineers working around the blast holes close to the furthest small drill rig. These larger drill rigs, they need to be able to drill holes in excess of 15 meters, which is typically quite a normal bench height for open pit mines. And the benches are just those steps you can see in the background. After the holes are drilled, they're filled with explosives, typically explosives such as ammonium nitrate fuel oil or combinations thereof, and they're blasted. A short example. So this is really the first energy intensive stage in the mining process. And the main point of blasting is to fracture the rock mass. Once it's fractured, it can be easily mined out using a shovel. So after it's been fractured, you bring in a shovel and then start to remove the fractured ore and load it into a haul truck. Typically, mine schedulers look to be able to fill one of these haul trucks, which could be up to 300 plus tons, in about a minute, which normally takes about 4 to 5 bucket loads from a shovel. And typically mining engineers will go through a planning process and determine how big the shovel needs to be, how big the truck needs to be, and marry the two to create this truck and shovel fleet to be used on site. After being loaded into a haul truck, it's either hauled all the way to the processing facility, otherwise known as the mill, or sometimes it can be loaded onto a conveyor. There's normally a stage during pre-feasibility studies for mines where the miner will do an assessment and comparison between using a haul fleet or using a conveying system. Both have their positives. Obviously, haul trucks are very flexible. You've got a lot of redundancy. If you lose one haul truck, you've got the rest of the fleet to mitigate any kind of production loss. Conveyors, on the other hand, they can be very effective at moving large amounts of tons at very fast rates. But in terms of a risk profile, it does introduce a single point of failure. And we've seen multiple losses relating to both haul trucks and conveyors. But it's typically the conveyors that lead to larger business interruption claims, as it can't be mitigated as easily as the loss of a single haul truck. And after that, we move on to the mill and the processing circuits. I'll go through processing in a bit more detail shortly, but now I'll just briefly cover underground mining. As I mentioned, a lot of these topics could be standalone presentations, and underground mining is no different. It's typically more complex than open pit. There's a lot more risk associated. it's a lot more planning around the geotechnics and the rock stability that's required, in addition to ventilation, which is less required on surface. There are multiple different methods available, typically paired to the commodity type. This example on the right-hand side is sub-level stoping. This is commonly used for heavy metals with high value. It's quite a targeted underground mining method, so it requires a valuable commodity to be profitable. Mining methods such as longwall mining or room and pillar are a little bit more simple, and they are slightly cheaper to implement, which allows a miner to mine a lower value commodity such as a seam deposit like coal or phosphates or salts, but they require very regular ore bodies of certain dimensions, and in particular they have to be quite flat and over a large area. And finally, just going to look at block caving in a little bit more detail. Block caving is a mining method that we're seeing used more often, and typically by the majors. We see block caving in Australia, Canada, and recently in Asia. We wanted just to bring it up today because it's a mining method not only are we seeing more often, but we believe it's going to continue to be deployed more often. And the reason for that is the average grade of deposits around the world, ore deposits that include gold, copper, silver, is declining. All the high grade, easy to access surface deposits have either been found or they've yet to be found, but they are potentially in very difficult regions or areas to extract from. So what's left are these deeper, lower grade ore bodies, which require a bulk mining method to be mined economically. The issue with underground mining is typically it requires quite a high grade deposit to make it economical. But as those high grade deposits are no longer easily available, this is a mining method that could be used to mine on a very large scale a low grade ore body. It differs from the previous sub-level stoping mining method that I mentioned, mainly around the amount of development that's required prior to any production taking place. And you can see in the images I have, there's a lot of underground developments below the block, and the block is that fractured grey, light grey, dark grey area. The reason why this is it's still a relatively new mining method is because of the cost. It's very expensive to set up all the required developments prior to any production occurring. So there's no cash flow coming in for sometimes 2, 3, 4 years of the actual development of the underground workings. But once it is operational, the block effectively collapses in under its own weight. So it's blasted in the same way that in open pit or underground, the first stage is blasting. But after the first stage blasting, typically there will be no more blasting for the life of that block cave. After the first stage of blasting, where mining is undertaken essentially underneath the block will start to collapse in under its own weight and causing its own seismicity. We had a claim in Australia a few years ago on a block cave operation, and seismicity was front and center of that claim. The caving operation requires seismicity, but on this occasion, the collapse got out of control and the mine was experiencing high levels of seismicity above what they forecast, which is quite a difficult thing to present to an insurer. It's a mine that requires seismicity and they're making a claim because they have too much of it. But that's just one of the complexities around block caving. Underground mining equipment, pretty much the same as open pit. We have drill rigs, we have trucks and shovels, but as you can see, they're low profile, they're designed for the environment, which is quite a tight spatial environment. Conveyors are very popular underground, more so than locomotives. Typically they've been replaced by conveyors, normally because locomotives were typically powered off diesel generators, and diesel fumes underground requires more ventilation and more cost. It's a very quick run through of open pit and underground mining, you'll appreciate, but just want to move on to processing. Processing really starts off with the reduction in size of a particle, or comminution as it's referred to. The first stage in size reduction is the blasting. So I mentioned it before, fracturing the rock mass is the first stage in taking one rock in situ and then breaking it into a workable size that it can then be processed. So a lot of time and effort and engineering will go into designing a blast plan to maximize the fracturing of the rock mass, so that when it comes to the crushing and grinding, it's of a regular size, and it means that the crushers and the grinders can work most efficiently. There are a number of different crushers, and in a complex mine processing environment, you might have a primary crusher and a secondary crusher, sometimes even a tertiary crusher, before you move into grinding. Just got an example on the left-hand side of a cone crusher, but those familiar with mining claims may have seen jaw crushers or gyratory crushers. Each one has its own particular niche, but typically it's the simple act of crushing rock from one size down to another. After crushing, the main difference between crushing and grinding is typically the addition of water. To continually move ore through a processing circuit, it's a lot easier to do if that ore is in a slurry, in a liquid form. It can be pumped, whereas if it's dry, it has to be conveyed. So after crushing, typically water is added into the grinding circuit. We see a large number of claims relating to mills, and the example I have on the right-hand side is a SAG mill. Typically, SAG mills, semi-autogenous or autogenous mills. The difference between the two is typically just the addition of a grinding medium, and that grinding medium is just iron rods or iron balls, which just promote increased grinding whilst being turned in this drum that you can see in the image in the top right-hand side. And that drum is about 8 meters in diameter. So there's huge forces, but having to be turned at a very slow rate, which requires quite a complex gearing arrangement. And we typically see claims relating to that gearing and claims relating to the teeth on those gears, which are under very high stresses. After grinding, it's just a simple stage of classifying. I have an image of a hydrocyclone here. You can see it here in the animation that the smaller, lighter particles are moved through the top of the cyclone, and the heavier, denser particles fall to the bottom. The denser particles can then be reintroduced to the grinding circuit to make sure that they're of the correct size before moving on to liberation. And liberation, again, could be a topic in itself, but just an example in gold, we see heap leaching very often, and that is taking the ground material, the ground ore, and spraying acid across the top to dissolve the target commodity, and then collecting the dissolved leachate, which is then stripped back to produce gold. Another method of liberation is froth flotation. Froth flotation, I've seen it used typically on lead and zinc operations, and it's a similar process. It's really for just concentrating that ore to a higher degree, typically to around 60 or 70% of the target commodity, and it's done so by pumping the slurry ore into a flotation tank. The tank is then agitated, and it's agitated through, you can see here the agitator at the bottom, whilst mixing in a substance called a surfactant, which effectively causes the ore to bubble, and the solution ends up being this bubbly, heavy metal rich froth, which can then be stripped away from the top of the flotation tank and then dried out into a, as I mentioned, 65% cake substance, which can then be sent off for further smelting and refining. And then to put it all into context, this is a typical process flow sheet. And I'll just briefly talk you through, starting on the left-hand side, you can see those 3 triangles. They're the stockpiles, so that is piled ore taken directly from the mine before it enters the processing circuit. As an adjuster, if we're notified of a claim on a mine in the processing circuit, we'll always ask for the process flow sheet, because we need to understand where does the piece of equipment that's been damaged fit into the bigger picture. And not only where does it fit in, will it cause a complete stoppage of production? Or, for example, are there multiple mills that one can be run whilst one is stopped? Are there multiple tanks? Perhaps that can be rerouted. So we always start off with the process flow sheet. And looking at those stockpiles, you can see the first arrow up to a crusher. From the crusher, we move on to grinding. There's a simplified grinding circuit with a cyclone, which is used, as I mentioned, just to check that the ground ore is of the correct size. After that, in this case, they're using a flotation circuit to actually float off waste materials, carbon and sulfur. If you float off waste materials, you're left with a more refined target commodity. So in this case, it's gold. The remaining gold concentration will increase if you've removed other waste products. Just skipping through to the bottom left-hand side, you can see the leaching circuit. As I mentioned before, in this case, it's cyanide being added to the remaining gold ore, and then the collected leachate is then won back using electrolysis. With a gold mine, typically we see grades of 1 gram per ton. So a miner will go through all this effort for 1 gram of gold per ton of material mined. That's a lot of waste. That remaining effectively a ton has to go somewhere. If it's an underground mine, the first step is usually to try and pump any waste back underground. Because of how material swells after it's been mined, after it's been taken out of situ, typically you can never get all of the material back underground into the void that it was originally mined out of. So it has to be stored on surface. And it's stored on surface in tailings storage facilities. These are obviously a hot topic in mining at the moment, and obviously in the Canadian market after some recent losses. Just again, very briefly touch upon TSFs. There are 3 main construction methods for a TSF, the upstream, the downstream, and the centerline. In the simplest terms, the upstream method is seen in the top image, starting off with a single starter dike, and then lifts are built on top of that first dike and on top of tailings that are deposited into the dam. So in the image, the white rhombus on the dike is the dam, and then the shaded black and white grey area are the tailings. So once the starter dike is in place, tailings are pumped into the TSF, and when they reach the height of the first lift, a second lift has to be added, and again, and a third. The issue with the upstream method is you can see the lifts are built not only on the first dike, but also on the tailings themselves. And this is an unconsolidated material. There's no additional settling agents like cement. It's just pumped in tailings that are dried out. The downstream method, you can see here the starter dike in the same position, same size, but then each additional lift gets larger. In doing so, there's no building on top of tailings, which potentially increases the stability, the strength of that dam wall, but it's more costly. And at this point, the mine, this is storage of waste. There's no benefit to them spending more money if they don't have to. So the upstream method has been very popular just because it's cheaper and it can be built more quickly. So it provides more tailing storage space. But what we're seeing over the last 10, 15, 20 years is that catastrophic failures seem to be more associated with the upstream method, and there is talk of whether or not the upstream method is still suitable. We're seeing a combination of the upstream, the downstream, and the centerline, which is just a hybrid of the two, potentially starting off with downstream construction and then finishing with upstream with the upper lifts when that stability is already ingrained in the structure itself. And this is just a quick example of what a constructed TSF might look like. I think with that, we go to a poll. And the poll, true or false, Canada has the world's largest tailing pond. So I'll just give you a few seconds just to look at that. Okay. And the results. 65% true, 35% false. Well, it's true. It's a Canadian mining webinar. It would be rude for it not to be true. It is the Syncrude Mildred Lake settling basin, which has 18 kilometers of dam walls at a height of between 44 and 88 meters high. Right, I appreciate that was a very quick start to finish open pit underground mining, processing and tailings run through. But now we move on to claims. And just to kick off, I'm just going to have a quick recap of some of the impacts COVID-19 has had on claims that we've been handling. Typically, insureds have been very reluctant to allow people to site, adjusters included. Obviously, minimizing the movement of people has been key to stopping the spread of COVID and impacting business operations. Through this, we've seen issues getting OEMs to site to conduct repairs, and that ball mill loss that I mentioned before was one example where the OEM was based in Australia. Australia has one of the strictest border restrictions in the world at the moment, and they couldn't send people from Australia to the mine in Southeast Asia to install a girth gear. That threw up questions as to whether, if we were to get a third party to install it, whether that would void the OEM's warranty for the installation. But the mine was running at some $500,000 a day gross profit loss, and when those numbers are on the table, solutions can be found. Outside of that, just generally access to skilled labour and the movement of skilled labour has been difficult. Also with the introduction of quarantine requirements, it's extended repair campaigns, and also made it more difficult to make up losses. As an adjuster, we're always asked the question by insurers whether or not an insured can make up losses. It's a lot more difficult when you can't send more resources to sites. If you can't bring in more equipment, bring in more people, bring in more labour, it becomes more difficult to make up losses. And there's been an impact to commodity prices. Some have fared very well, some less so. And just an example on some production impacts, we have losses in Poland. PGG and JSW, the state-backed coal producers in Poland, they had to close 12 mines for a month in June last year because some 3,000 of their 80,000 employees caught COVID on site. And with that, I'm handing over now to Dallas.
Good morning, good afternoon, everyone, depending on where you're located. I'm going to kick our claim example section of the agenda off with 3 different claim examples that I've been involved with, and then I'm going to pass it over to Brian. So in my part of the world, in Alberta, a lot of our mining operations are actually connected to oil production as well. And that's related to our oil sands in Alberta and into Saskatchewan. Roughly about 140,000 square kilometers of our northern boreal forest is oil sands reserves, 165 billion barrels. And about 20% of those reserves are within 70 meters of the surface. And for those areas, typically the operators are mining the ore through a fairly standard open pit mine. So consequently, given where I'm working here, a lot of my losses and my experience relates to these oil sands and mining operations. So this first example that I'm going to talk about is an oil sands operation. The loss involves the tailings aspect, and it involves a thickener wall collapse. By way of background, a thickener is used in mining for the tailings. It helps, it's a big tank, and it's basically has a large rake at the top that stirs the tailings mixture. And the idea is to promote separation of the sand and the water, and it makes it more efficient and reduces the size of the tailings because they're able to reuse the water and just send the sand. So this particular loss, the operator was looking to expand their tailings thickener, and the photograph on the right-hand side shows 4 tanks that were being constructed at the site. They're massive. They're 70 meters in diameter and about 16 meters high. The loss itself involved what's known as a mechanically stabilized earth wall, which is effectively the base beneath the tank, and I'll provide a bit more description about what happened. But it was, of course, a construction loss. Both the owner and the general contractor advanced separate claims, and combined, those claims totaled about $120 million Canadian. Just a bit more background, just for understanding how the loss occurred. This is a simplified schematic of what the thickener tank would look like. The light beige color at the bottom is below the surface of the ground, and basically they excavate down to the bedrock and then backfill that area after they install a pump house. The whole tank is set up so it slopes towards the center, so that promotes the sand running out through the center of it and then being allowed to be pumped out. The loss itself occurred on this MSE wall, which, if you can see the light colored yellow at the perimeter, it's about a 10-meter high wall. These walls are very similar to what you see if you're driving down the road and you go through an underpass and you'll see concrete blocking that's interconnected. It's the same sort of idea, and it's constructed by placing various lifts of backfill. In this case, it was limestone. They were placing it 750 millimeter lifts and building it up and compacting as they go. And the concrete block walls are then fixed to the backfill through strapping. And it was a collapse of that concrete blocks that led to the loss, as you can see in these photographs. The blocking broke free, allowed the backfill beneath it to come out, and the walls collapsed. This was about 1.5 years into the construction project, and they were they were working on the tank base itself and to construct the tank when these failures started happening. There were 7 different failures involving 2 of the tanks. The policy itself, the policy itself was a COC cover, just property damage, no time element aspect, no delay in startup or time element coverage. It was a challenging claim for 3 different reasons primarily. Firstly, the cause investigation was difficult, was technical. We involved structural and geotechnical engineers to investigate. Obviously, we needed to determine the cause to know if we had a coverage trigger into the policy. They did an extensive investigation over several months, determined that the cause was faulty workmanship and materials. And from all claims people on the line will quickly raise flags on any claim, but in this instance, it was a Leg 3, London Engineering Group 3 wording, which is the most broad form of defects cover. Effectively covers the defect, just excludes any betterment. So despite the fact that we had a workmanship issue, it was a covered, determined to be a covered loss. The other challenging aspect of the claim was that the owner and the general contractor did not like one another very much, and the relationship was getting worse and worse through the project and really deteriorated when this wall collapse occurred. So they were not communicating well, were very adversarial and dealing through their lawyers. And for us as the adjusters investigating on behalf of both parties, who were both equally named insureds under the policy, it made it really challenging to deal with the claim. And one of the big challenges was that they rather than trying to identify what might be covered under the policy and making the claim for that, they basically collected all their costs. So the repair costs, the delay impacts, and everything, combined it all together and submitted it all. So it was through to us to separate out what might be covered and what might be not. It was a large claim, so lots of data to go through that we worked with a cost consultant for a couple of years to sort out. We did do the adjustment, determined what we thought was fair to be indemnified. There was still a dispute, particularly with the general contractor on some of the coverage decisions, various discussions about the coverage and legal interpretations, but ultimately it did get concluded on the basis of a compromise settlement based on evaluating litigation risk. Get you to flip to the next one, Andy. Okay, so my second example, again, an open pit mine. This is in an oil sands context. It's an equipment loss. It's a reasonably straightforward loss, but it involves the size and scale of this equipment is worth mentioning. In the oil sands operations, mining operations, until about the 1990s, most of the operators used massive drag lines and bucket wheels, which, as Andy pointed out earlier, you've got one large piece of equipment that if it goes down, you don't have a lot of redundancy built in, so it shuts you down. So in the 90s, there was a big switch to move to shovels and truck fleets rather than these single pieces of equipment. And this particular loss involves a large Hitachi shovel. It's actually reported to be the largest shovel that they make. It's roughly 3 stories high, 40 meters in length, 825 tons, and the bucket alone has a capacity of 40 cubic meters, which, as Andy pointed out earlier, is about 5 bucket loads or so to fill one of these large mining trucks. What really hit it home for me was when I looked at the size of the fuel tank on this unit. It's 15,000 liters, which for an average size car, that's over probably 225 to 250 fill-ups of a regular car in one fuel tank on this particular unit. The shovel, as I mentioned, is working in the open pit. It was working along one night during the winter, up against the face of the wall. The operator was just scooping a bucket load, and as he was doing that, he heard a loud pop sound. He looked out and immediately saw a pretty intense fire that was developing. Smartly, he evacuated immediately because the fire was very close to the cab and ultimately destroyed the cab. These units typically are equipped with onboard fire suppression systems, and in this case, it did activate, but the fire had a significant amount of fuel right away. As you can see, it was very intense, and it just overwhelmed the suppression system. It wasn't effective in putting the fire out. The insured has its own fire department. They did attend, but by the time they got there, the fire was very advanced, and they were able just to control it and ultimately put it out. A cause investigation was done. Given the circumstances, and report from the operator was thought to be most likely to be a hydraulic hose that ignited or failed, released oil and ignited on a hot surface on the engine. But like most fires, a lot of the evidence is actually destroyed, so there was no conclusive finding. The damage was significant. Basically, everything above the tracks, the car body, above that car body, so the main deck, which includes the engines, the hydraulic systems, the electrical systems, the cab, was all destroyed because of the intensity of the fire. We worked with the owner, their vendor, and we had a heavy equipment appraiser involved to do a thorough assessment of the damage and repair costs. They worked together to come up with that. Ultimately, it was determined, the thing that pushed it over was that the main frame was ultimately determined to be distorted because of the heat. So the repair cost came within about 5% of the replacement cost, which is about $20 million Canadian. We We did work with the owner because they have a fleet of these units. We negotiated on the salvage. There was some salvageable components, the bucket and the boom and some other things. We negotiated a salvage value of $1 million roughly. That was deducted, and the unit was deemed a constructive total loss. We did look at it subrogation, but again, without a conclusive finding on the cause, it was ultimately abandoned. My third example does not involve oil sands, but does involve a open pit gold mine. It's not a loss that occurred in Canada, but was a mine owned by a Canadian company. It was located in Central Asia, up in the mountain ranges, a very high elevation, 13 to 14,000 feet above sea level, which to put into context is Everest Base Camp is around 17,000 feet above sea level. So it's the elevation made the mining environment quite challenging. The mine itself produced about 700,000 ounces of gold per year. It was a standard open pit mine, as Andy covered, a cycle of drilling, blasting, excavation, and hauling. The mine started at the 4,300 meter level above sea level, and at the time, and the way these things are mined, they do them in a series of cutbacks. So they were on their fourth cutback and had mined down to the 4,000 meter level, and were just above a rich ore body when the loss occurred. A couple of photographs just to give perspective. You can see on the left, this is a before photo. You can see the benching, as Andy mentioned. The loss itself happened during the summer. A pretty typical work day. They were drilling some for blasting. They saw some instability on the side of the pit wall. Some rocks started falling down, became concerned, evacuated, and within about 15 minutes, the toe of the wall came out, and the whole face collapsed about 250 meters across by 280 meters tall. So an estimated 7 million tons of rock came sliding down the wall. The claim had some fairly straightforward aspects and then some difficult aspects. The straightforward aspect was some equipment that was damaged, some drills. You can see an example. Pretty clearly, you couldn't reuse that to repair that drill. It was destroyed. About $2.5 million worth of equipment was destroyed. The challenging aspect of this claim was this, all the debris and rock that basically covered and obstructed access to the ore body. So the mine was forced to go back to the top of the pit wall and start mining from the top down with no cash flow or recoverable ore. It's just they're removing rock to get back down to where they were mining before. So they incurred some increased mining costs, and they also had a business interruption loss, which they estimated at about $80 million. This was a complex placement on the coverage. There was a captive insurer with a fronting company and various layers of reinsurers. The challenge was really that the policy had not been agreed at the time the loss occurred. The insured took the position that the pit wall was actually insured property and advised that they declared values for that pit wall. The insurers didn't agree, relied on pit exclusions and our intention, at least, for pit exclusions and land exclusions. And there was quite a bit of discussion and back and forth, and again, just made really difficult to deal with the claim without the agreed wording. Ultimately, after discussing it for a year or two and some legal interpretation, the two parties settled for a compromise settlement based on a percentage of the amount claimed in order to resolve the claim. And with that, that's my three examples. Now I'm going to pass it over to Mr. Aston to talk about his.
Thanks, Alice. Good morning, everybody. Good afternoon. I got the easy part of this. I've just got one example to provide to you. My mining experience has been in northern British Columbia, Alaska, and Mongolia. The particular claim I'm going to present, which is a short presentation, relates to a tailing pond collapse. It is headed up Mount Poly Mining Corporation, as you will see from the slide, and we have no objection to that name being produced, as we have passed the limitation period, and there is no legislation outstanding, so that just remains okay to mention. But this happened in 2014. It was the loss was a huge tailings pond, which not quite as big as the one in Alberta that was mentioned by Andy, but still very, very large. And the claim itself was in the region of about $150 million Canadian. Our involvement, however, was limited under the coverage side of it, because we were the primary policy, not the liability policy, and as a result of which, and I will go into the causation at the end once I give you the story, but as a result, the primary policy clearly was exhausted, and it was paid out. I had hoped there to provide for you, and I did have photographs, but just because it's actually quite long ago, but where the arrow is, there was a 300-ton dump truck, which actually just looks like a Nant. So just to give you an idea, that is the center of the tailings pond after all the tailings had released through that gap in the middle where the arrow is. And just as a way of explaining it to you, it's estimated that 6 million cubic meters of soil is associated with this dam collapse, releasing approximately 10 cubic meters of water into the habitat, causing a silting at Poly Lake, which is down the way, and flowing down into Hazeltine Creek and into Quesnel Lake, which you can see on the top right-hand corner. Quesnel Lake is a very, very deep, probably the deepest lake actually in British Columbia, and it's environmentally sensitive. So all this tailings pond flew down this bank and into the lake. The accident at Mount Poly released sediments contaminated mostly with arsenic and heavy metals, including lead, calcium, and mercury. At this time, at that time there were ongoing environmental studies, but as I said at the outset, no charges were laid, and the limitation period has now expired. This is an open pit copper gold mine incorporating and developing underground mining projects. Essentially, ore is mined from the open pits and hauled to the main crusher. The crusher process, which is similar to what Andy was talking about, includes stages involving 5 crushers, 20 conveyors, and 4 sets of screens. The one is dumped into the feed pocket of the primary crusher, and the product is discharged to the grinding circuit with particles of a diameter of 20 millimeters. The product is then split into 2 ball mills, one for larger product and one for smaller product. Particles are then dumped to a flotation circuit, which separates the valuable material from the waste material. Thereafter, concentrate is dewatered and stored for shipping. The copper concentrate is trucked to the port of Vancouver, where I live, and shipped to overseas smelters. The balance of the tailing go in to the tailings pond. in this particular instance, and I can be quite brief about this, our concentration there was really because we were the primary policy, not the liability policy, was try to determine what was the failure. Apparently, it was a design flaw that resulted from unknown issue in the foundations. A clay-like layer in the foundations was not fully known or understood. And just as a way of an example, I think somebody said it to me when I was there at the time. It would be like going to the beach and building a sand castle and just keeping on piling the sand on top of the sand on top of the sand without extending the base outwards. So it eventually just falls over. And that is essentially what happened here. As they poured the tailings into the tailing pond, they increased the height of the tailing pond around the edge. And I can't recall exactly the size of the tailings pond, but it was huge. But they never actually reinforced the foundations. As a result, it breached, as was shown in the first photograph that Andy put up there. It breached and flew down the mountain to Quesnel Lake, and there it is. As I said, we were just the primary policy, and insurers in this instance decided it was best to cut and run, and payment was made under the primary policy, and that's the extent of it. But that was one of the experiences that I have had of many in British Columbia, and that's in the central part of British Columbia. And that really, I think, brings this section to a conclusion. I'm going to hand back to Andy or Robert.
Brian, it's back to me. I appreciate we're now getting a little bit pushed on time, so I'll just skip over this. The last example, we're moving away from Canada. This is Australia, as you can see by the very red-looking outback. And just another issue that we find with mining claims. Mines are typically located in the middle of nowhere, and they require either lengthy trucking operations, or in this case, rail, to get their product from site to port to be sold into the market. This is a heavy weather event which resulted in the washing out of ballast underneath this rail line. The train, you can see here, was unloaded. It was returning from port back to the mines to be reloaded, and I'll just pause it here where the derailment occurred. On its way back, it derailed because of the flooding. And the points that we just wanted to bring up here, whilst this was a sizable claim in itself, we were instructed on behalf of one of the mines which uses this rail line to get its product to port, and it was a contingent business interruption claim. One of the interesting points around this claim was this rail line serviced a number of mines. This is quite common. Deposits typically can be found within a similar area because of how they're formed geologically. So what you have is 3 or 4 different mines all relying on the same rail line to ship their products to port. And here is just an example of Queensland, and you see the rail lines spidering across Queensland, servicing a number of mines. So with the contingent BI claim that we were instructed on, it ended up being in the region of about 25 million Aussie dollars. But the insured tried to mitigate their loss by trucking concentrate to port. However, the 4 other mines which also relied on this rail line had the exact same plan. They were also looking to truck their concentrate to port. What we ended up with was effectively a bidding war to get trucks and to continue normal business operations. It ended up not being economical to use the trucks simply because the demand pushed the price too high to make it economical. So that's really just something we want to point out specific to mining claims and how contingent BI claims arise. And now just to wrap up very briefly, mining claims are complex. That's probably not news to anybody here. Our main goal is to understand the main issues early on in the process and seek simple solutions. Typically, mining BI claims come down to the number of tons and the grade of those tons, and then it's a simple profit calculation exercise. I say simple, but I'd have to do it. Most losses, most BI losses we see can be forecast to within about 90% accuracy in the first 3 months. And then we spend another 6, 9, 12 months after that calculating the final 10%. But if we can get early understanding through open and transparent work with the insured, we can typically expedite the settlement of claims where possible. Sometimes they are complex and they require external consultants, which we appreciate. When we do bring in external consultants, geotechnical engineers, professional mining engineers, it is useful to keep the brief well managed and make sure that the scope is understood. We want to only be asking the questions that are relevant to the insured that will progress matters and hopefully lead to either an equally acceptable or equally unacceptable settlement for all parties. And just finally, just to focus on the key issues and proactively engage. And with that, I think I'll pass back to Robert.
Perfect, thanks, Andy. So we do have a question in here, which is for you, and that is upstream expansions of TSF relies on proper consolidation of tailings. Is your statement that upstream is quicker than other methods based on experience on particular minerals or extraction processes?
The statement upstream is quicker, typically within, I meant it within the design and construction of the lifts. So when you're comparing an upstream lift to a downstream lift, it's less material and the movement, the bulk movement of material can be done quicker just because there's less volume to move. That was specific just to that point.
Perfect, thanks for that. And I guess you guys really covered every point fantastically, because that was the only question we've had so far. So if there are any more questions that come in, we're happy to get those answered and send those out to you as well. There will be a follow-up email, which will include a link to the actual presentation itself. It will include the bios of the presenters, and that will be sent out likely tomorrow or the beginning of next week. And then if we could just flip to the slide that has the continuing education email address, which I'm sure everybody is wanting to see, that would be great. And so with this one, if you can send an email to Jada Williamson at the bottom there, please. And as I mentioned, include your CIPR numbers. That would be great, and we will make sure that you get your certificates. For other provinces that aren't listed there, where you just need a generic certificate, we can also produce those for you as well. So please send those over, and we're happy to get you the CE credits. As mentioned at the beginning of this presentation, we are going to be hosting many more webinars throughout the year. The next one is coming up in a couple of weeks, and that's on trade credit. So we're really hoping that we're able to provide you with the CE credits that you need throughout the year. So we very much look forward to seeing you all on the next one. Another big thank you to Andy, Dallas, and Brian for the presentation. It was excellent. And for everybody that attended, thank you.